Hi, my name is Kalle Rutanen. This is On Notation in Algorithm Analysis, Part 1, Linear Dominance. These videos are based on the following publications. The first is my doctoral thesis, which is peer-reviewed and comprehensive. The second is a journal paper, which is peer-reviewed and brief. The third is a version in arXiv which has the latest results but looks bad because arXiv has old LaTeX packages. And the fourth can be automated from my homepage, which has the latest results and also looks good. Let's begin. A problem is a function from a set x to a set y. The set x is the input set, while the set y is the output set. Here's an example of a problem, a searching problem. Given a sequence of zeros followed by a sequence of ones, find the smallest index which contains 1. Here's such a sequence. In these slides, I will also give a formal description of everything I say, but I will be skipping over these, and if you want to, you can pause over them to see them more detailedly. One way to solve the searching problem is linear search, where we just scan from left to right the numbers until we hit the first one. In Python, you would implement it like this. Here's another way to solve the searching problem, an exponential search. In this approach, we take doubling steps towards the ones until we hit the first one, and then trace our way back by halving the steps. If we get to 0, then we do not take the step, but halve the step and until we get a 1. In Python, you would implement it like this. A cost function tells for each input of the algorithm how much resources the algorithm uses for that input. If we are interested in the number of sequence lookups in linear search and exponential search, then those are given by these functions, these cost functions. So the linear search is almost linear on the position of the first one, and the exponential search is logarithmic on the position of the first one. And if we draw a graph, we see that the exponential search seems much better on solving the problem. However, there are two exceptions where exponential search uses one additional resource units compared to linear search. So we cannot quite claim that the exponential search is always better than linear search. But it seems that exponential search is an essential way better than linear search. Can we formalize this term, essentially better? We can. We do this by a dominance relation, and this relation works on functions with values on non-negative real numbers. This dominance relation has certain properties that we will list next, and it formalizes what we mean by a cost function being essentially better or equivalent to another. We read the relation as is dominated by. there's a subscript in the relation x. It underlines that there is a dominance relation for every input set x. We can also define these related relations. The first one is read as f dominates g. It's a reflected version of is dominated by. F is equivalent to g if f is dominated by g and f dominates g. F is strictly dominated by g if f is dominated by g and f is not equivalent to g. F strictly dominates g if f dominates g and f is not equivalent to g. These are the properties that the dominance relations should have. There are 8 of them, and the first one is order consistency. If an algorithm A never uses more resources than algorithm B, then the cost function of A is dominated by the cost function of B. For example, for linear search and exponential search, we can show that the cost function of exponential search is at most 2 times cost function of linear search. By order consistency, the cost function of E is dominated by 2 times the cost function of linear search. We would like to show that the exponential search, the cost function of exponential search, is dominated by the cost function of linear search. However, we cannot do this yet, at least by order consistency, because there were those two exceptional sequences. The next property is transitivity. If f is dominated by g and g is dominated by h, then f is dominated by h. The next property is scale invariance. So suppose we modify the linear search a bit and do some redundant work. In the while loop, we test the indicator additional time, although we don't need to. This increases the number of sequence lookups to 2ks plus 1, whereas it used to be ks plus 1. So it's almost 2 times by just adding 1 line. Since it's so easy to make multiplicative changes to an algorithm, we declare that those changes are not interesting to us. So if we multiply a cost function by a positive real number, then we say that those multiples are equivalent. So recall that we analyzed that the cost function of linear search and exponential search were these functions, a linear and a logarithmic function. We already noticed that the cost function of exponential search is at most is dominated by 2 times the cost function of linear search. Then by scale invariance, we have that 2 times FL is dominated by FL. By transitivity, F is dominated by FL. So we now have a sense in which exponential search is essentially better or equivalent to linear search. Its F is dominated by FL according to any relation on these cost functions, which satisfies order consistency, transitivity, and scale invariance. But how about essentially better, without possibility of equivalence? We would like to show that exponential search is strictly dominated by linear search. We already know that exponential search is dominated by linear search. So it's sufficient to show that FE does not dominate FL. So if we define a trivial relation which holds for every pair of coast functions, then we have all of the desired properties this far. So this tells us that it's not possible to prove non-dominance yet. The next property is one separation. It says that there are at least some coast functions which are not equivalent to each other. And this will close off the trivial relation as a candidate for a dominance relation. So one separation says that the linear function n is not dominated by the constant function 1 when the domain is the positive integers. If we use the desirable properties as axioms, then every proof of f is dominated by g must appeal to order consistency. And every proof of non-dominance must appeal to one separation. All the other desirable properties propagate dominance and non-dominance in a structure-preserving manner. Although one separation excludes the trivial solution, we still cannot prove that FE does not dominate FL. Scale invariance and transitivity are too weak to propagate one separation into this case. The next property is subcomposability. And to study these next properties, we introduce a new problem. The array searching problem asks to find a zero-based index of the first element, which is at least 10 in a finite non-decreasing sequence of numbers. And formally, it's this. Here's an algorithm to solve the array searching problem. It uses the linear search. Here's another algorithm to solve the array searching problem. It uses exponential search. In either algorithm, we map a finite sequence through a function s, which maps z to x, where x is the input set required by the linear search and exponential search, and then perform a search on the mapped input. If we now analyze how many sequence lookups linear array search does, we have that it's given by a composition of FL and S. For exponential array search, it's given by the composition of FE and S. Intuitively, subcomposability says that if we substitute a better or equivalent sub-algorithm in a sub-algorithm call, then we get a better or equivalent algorithm overall. We already showed that FE is dominated by FL. By subcomposability, exponential array search is dominated by linear array search. The next property is locality. Here's another way to solve the searching problem, the array searching problem. In this algorithm, we pick either linear array search or exponential array search, depending on whether the array has odd length or even length. Here is the coast function for case array search. It's a piecewise function which is partitioned by whether the sequence is odd or length. Here's an improved version of the case array search. In this version, we have replaced the linear search with exponential search. So actually this is equivalent to just doing exponential search, but the casing is still there. And the coast function then is the same as the exponential array search. Intuitively, locality says that if we substitute a better or equivalent sub-algorithm on a subset of the input set, then we get a better or equivalent algorithm overall. For example, if we substitute exponential array search for linear array search on the A0 subset of case array search, then we get a better or equivalent improved case array search. The next property is subhomogeneity in N. Here's another way to solve the array search problem. A looped linear array search. In this version, we again do redundant work. We loop on the linear search and do this n squared times, where n is the length of the array. And here's the same thing, but using exponential array search instead. The coast functions for these looped versions are here. They are given by the coast function of the underlying algorithm times square of the length of the array. Intuitively, subhomogeneity in N says that if we substitute a better or equivalent sub-algorithm in a loop, then we get a better or equivalent algorithm overall. For example, if we substitute exponential array search for linear array search in looped linear array search, then we get a better or equivalent looped exponential array search. The last property is subhomogeneity in 1 per n. Intuitively, if an algorithm A in a loop is dominated by an algorithm B in a loop, then A is dominated by B. And now we have all of our desirable properties for the dominance relation. Let's think about these properties for a while. Subcomposability, locality, subhomogeneity in N, and subhomogeneity in 1 per n are structural properties. They all say the same thing, that if we substitute a better or equivalent sub-algorithm, then we get a better or equivalent algorithm overall. Suppose some structural property does not hold, then in at least one case we get a worse or incomparable algorithm after substituting a better or equivalent sub-algorithm. Neither case is unacceptable. So structural properties are necessary. Well, locality can be proved from the other properties. However, the remaining properties are minimal in the sense that no property can be proved from the others. Linear dominance is a relation on the coast functions defined by f is dominated by g if there exists a positive number c, so that f is at most c times g at every point. An example. Since f is at most 4 times g, we have that f is dominated by g in the sense of linear dominance. Linear dominance satisfies all of the desired properties for a dominance relation, as we listed them. There are no other solutions for a dominance relation. Dominance is linear dominance. Finally, we can show that exponential search is essentially better than linear search. We already know that f is dominated by fl, so we only need to show that Fe does not dominate Fl. By linear dominance, Fe dominates Fl is equivalent to Fl divided by Fe being bounded. Since Fl divided by Fe is unbounded, Fe does not dominate Fl. O notation on an input set X is defined by Oxf is the set of coast functions which are dominated by f. O notation on X contains the same information as the dominance relation in that same set in another form.